Well, good day, everyone. I want to welcome you to my lecture today. Of course, the focus today will basically be on regression discontinuity design. Give me 1 second. I'm actually going to share my lecture slide. Okay, so like I said, the focus is going to be on regression discontinuity design. They actually abbreviate as how we did. In the outline, basically going to introduce the concept of regression discontinuity design, then couple with application. So, and I hope everyone is hearing me clearly. Okay, so, in the introduction, Um, of course, we got situation where we want to study, we actually want to be able to take, or maybe we're pursuing what I call a course a goal. And in the process, we actually want to know the effect of what's on what. And, in most of the situation, what we always do is just to actually partition or assign participants into different groups. Like we're basically going to have a control group and the experimental group where we use what I call the principle of randomization. In doing that, of course, we call that an experimental, design. That is, we call that, that's an experimental study per se. So, okay, so, you know, an example of such is, you know, there was an article published in December 10, 2020, in the Journal of, England Weekly Journal of Medicine, located in state of Massachusetts in the United States. The title of the article was Safety and Efficacy of COVID-19 Vaccine. Of course, it was actually reported that, vaccine, produced, manufactured by Pfizer actually have 95% efficacy rate. Of course, what Pfizer actually did, they actually look out for participants and they randomly assign them into two groups. There is a control group that we call the placebo group, and there's a treatment group that we call the vaccine group. So those in the vaccine group, of course, they actually give them, you know, first dose of vaccine, and after 3 weeks they completed the dose, and they also do the same to those in the placebo group, except that the placebo group actually received nothing. So in the end, they were able to, they compare the vaccine incident rates in, I mean, um, the incident rate of COVID in the two group, because what they actually did, they exposed the participants in the two group of to COVID, and they basically want to see out of those that were actually, you know, um, giving the vaccine in the treatment group, and those ones, that were not giving anything in the control group. They basically want to see how many of them were actually able to prevent the occurrence of COVID. So they actually get what I call vaccine incident rate, where they compare the vaccine rate in one group and the vaccine rate in the other group, and at the end of the day, they actually arrive at 95% efficacy rate. Now, in that situation, that is when they use the idea of a random, the principle of randomization in assigning our participant. But in a situation where that is not visible, which I'm actually going to give you an example, situation whereby we basically use a threshold. or a cutoff point to determine, which of the participant actually, get the treatment. Okay, in that kind of situation, uh, we're basically going to be referring to what I call, regression discontinuity design. So the regression discontinuity design is actually being used in statistics, in econometrics, the political science, epidemiology, and other related discipline. It's actually a quasi experimental, pretest, protest design that aims, to determine the causal effects of intervention, by assigning a cutoff or a threshold above or below which intervention is assigned. You get what I mean? And we believe that with the idea of, you know, regression discontinuity design, we'll be able to compare observations, lying, closely on either side, of the threshold. And they believe with that it should be possible to estimate, the average treatment effect in environment, like I said, in which randomization is not visible. So this idea was actually, given by a psychologist, Donald Campbell in 1960, and it has now been extended, to uh, other areas of study. So, like I said, there's basically going to be, even though we're looking at the effect of treatment, but the participant do not have equal probability of being assigned to different groups. So because we have a running variable upon which we basically make a threshold. Okay, it is that very threshold that will determine whether particular participant will actually get a treatment or not. And that was exactly what I'm trying to say. So situation where that's happened, where there's a threshold, created, that determine, the participant that receive treatment. Of course, that will follow what I call regression discontinuity design. So which means that will require a running variable, at which at a certain threshold we now separate the observation into the treatment group and the control group. So we have the variants of RDD. We have the sharp RDD, and we have the fussy RDD. So the sharp RDD is, the threshold that separate the treatment and the control group exactly. Okay, and we have a fussy RDD, so which is the threshold that influences the probability of being treated. And this is in fact, it's an instrumental variable approach. If you watch my last video or what we've done before on instrumental variables. So what we actually, this approach is more or less a approach for instrumental variable as well. Okay, so looking into the advantage of RDD, we have some assumptions that can actually be tested because we actually said we're going to have a threshold, right? That, partition participant into two groups, right? Of course, it may be of interest to actually, test hypothesis about individual close to the threshold. Okay, of course, if we got a threshold, right, individual close to it at the right side and individual close to that at the left side, we basically going to conclude they are basically nearly going to be identical, except for certain characteristics which are affected by the treatment. So which means, the prior to the treatment, the outcome should not differ between the treatment and the control group. So we expect that. I'm going to say that again, the prior to the treatment, okay, the prior to the treatment, we don't expect the outcome to differ between the treatment and the control group. You get what I mean? So, which means the distribution of the variable which indicates the threshold should have no jump around this cutoff value. So around that particular cutoff value, we do not expect to have a jump. That was the assumption that we have at the beginning. You get that, right? Okay, so we want to go into the regression discontinuity basic idea. I remember when Campbell in 1960 was actually talking about this idea in psychology. It actually applied that to evaluate scholarship program. Of course, in a scholarship program, the issue of randomization is not going to come in because there's going to be a threshold that they're basically going to use in deciding whether a particular person, that's actually write an exam, whether it's going to be given scholarship or not. Okay, so what about the poverty score? Okay, talking about the cut-off price, because there's always going to be a cut-off point. Like I remember when you want to talk about the income in the United States, you have the poor, the middle class, and you have the rich also, which means if I'm actually using the middle class to be a cut-off point, so my belief is just going to be that okay, below the middle class, of course, we're talking about poor, and above the middle class, talking about rich. Then what about the land area, like fertilizer program or debt relief initiative? Of course, I actually remember recently the president of the United States proposed what I call a student debt relief program. We got a student who actually obtain loans, to study in the US, and part of the manifesto of the President Biden, he said he was actually going to forgive, some of the loan, not all, but it's actually use a threshold, so which means it's not every student that's actually owing that will be that their loan will be forgiven because there's a particular threshold on that. Okay, so what about the age? The date, like age cutoff for pension, the date of birth for starting school. I'm actually gonna talk about the one for starting school, like in the United States, before you can actually start kindergarten. Okay, you're actually gonna read the age of 5. So what of in a situation, and that age of 5, you have to reach it by before September of the school year. So what of those who actually clock, September, I mean, who clock the age of 5, even, maybe 2 or 3 days after the school resumes. So definitely they basically not going to be considered. Understand that kind of stuff. Okay. So I think there are other examples like that under the elections, where you talk about the fraction that voted, for a candidate, of a particular party. Okay, so like I said, they actually proposing a density test, and in the density test, of course, the non-hypothesis is going to tell you, the continuity of the running variable, the density of the running variable, the continuity. That was what we said the other time. There was no any jump. Okay, that is not what the non-hypothesis is talking about. Okay, and the alternative is going to say, of course, there's a jump. Okay. Now, this is the model or specification. Maybe I'm looking at the relationship between Y and X, and this is what actually happened. The TI here is the treatment. So you basically want to test the treatment effect. You get what I mean? And to get people get into the, you know, we have a particular threshold that we place on the running variable, that we actually determine whether, um, some unit or some participant will get the treatment or not. Okay, so which I'm actually going to refer to X as a running variable. So which means it is not all the participant that we actually get the treatment. So here the treatment here is actually going to be categorical, depending on the threshold that was placed on X. So take a look at that. If Ti equal to 1, it means each subject I received the treatment, and Ti equal to 0, it means otherwise. And of course, whether they're going to receive the treatment or not, it depends on, you know, we're on the threshold. Okay, just like the example I cited the other time about those who we actually get, I mean, those students that, their student loan will actually be forgiven by the present administration, depend on whether they actually meet the threshold set. Okay, so which means some that meet the threshold set will be the one that will receive the treatment, and the treatment this time around is just like their student loan will actually be forgiven, and those that did not actually meet the threshold will not benefit from that gesture. That is exactly what I mean. And of course, the example I'm also going to be using in this study is the age, the drinking age in the United States. Like if I want to look at the effects of alcohol consumption on mortality. Of course, I also need to put into consideration the law in the US. Is just like, okay, the the drinking age before you can actually purchase alcohol, then you need to attain the age of 21. So which means in that situation, the 21 is basically going to be threshold. Okay, so in explaining the model specification once again, is basically still going to look like a conventional regression model where you have the error time, and of course the assumption also revolve around that. Okay, so then we basically need to centered, we need a centered at the cutoff point, and for us to do the centering at the cutoff point, we're basically going to subtract the cutoff point C from the running variable, and of course the moment we do that, the particular treatment effect that we basically going to have, the treatment effect is going to be the TI. So the coefficient of the TI, so which is the beta one. So take a look at that. So that would be the treatment effect that we're actually talking about. Now, we can actually find the conditional mean of the response, at the threshold. You get what I mean? Where T equal to 1. So that is going to be the beta naught plus the beta 1. And of course, where T equal to 0, and then the running variable equal to the threshold is going to be equal to beta naught. And of course, we are the expected value of y, this when we subtract that, of course, it's more or less like we're actually doing this guy minus this guy. Of course, we eventually going to have the beta one. Okay, well, so like I said, in this study, I'm actually going to use data set, used by Carpenter and Dopkin in 2009. And of course, they are actually trying to estimate the effect of alcohol consumption on mortality by utilizing the minimum drinking age within the regression discontinuity design. So, because we're talking about the United States, the minimum drinking age alcohol, has to be 21. So that is going to serve as a threshold. So if you want to do this in R, we actually need packages that we need to load. So which is the one I'm actually displaying now. Okay, so is there anyone want to ask question or who need some clarification? Okay, so it means you really get that. Okay, so part of the preliminary investigation that we do when we are trying to characterize relationship is just to generate a scatter plot, right? Now, in the generation of the scatter plot, I've put into consideration that 21, which is the minimum drinking age. I'm talking about the minimum alcohol drinking age, and the mortality rate is actually per 100,000. Until you know that, and of course, the running variable here is going to be age, and don't forget there's a threshold on age. Okay, 21. Okay, is a threshold. Okay, so this is a plot that actually came out of that. So where you have the response to be mortality rate per 100,000. And of course, you actually have the age, and of course you can see 21 here now. And as you can see here, this is like having two categories. Okay, so this is more or less like the mortality, okay, that occur before the drinking age of 21. This is the way the relationship is, and the relationship between the mortality and age over 21, you can see now. And of course, we the idea of, you know, uh, of a regression discontinuity design will come in because we actually have a threshold. You get what I mean? A cutoff point, right? And we use that in a quasi-experimental design. So which means not all participants, they don't have equal chance of being assigned to groups because it is the cutoff point that will determine that. Okay, so we basically going to test some hypotheses using either the idea of same slopes, the idea of different slopes, and not only that, we also going to consider two different kind of a functional form. And after that, we're going to look at the sensitivity of the RDD, regression discontinuity design, to when I don't use the whole set of data, and maybe I actually have a kind of truncation. But right now, I want to look at the idea of the same slopes, okay, on the both side of the IO. Now, this is the code in R, okay, that I'm actually going to use for that. And this is actually the result, okay. So if you can see, as you can see in the result now, the treatment effect, you actually focus on the estimate of the threshold, so which means the mortality, okay, of the participant here. I'm talking about in 100,000, okay, actually, the decreases, or, I'm sorry, it increases, it's 7.6627 higher, when the participant actually attain the minimum age of 21. Let me tell you something. That doesn't mean if you place a threshold of 21 for those who will have access to the alcohol in the state, that doesn't mean some that are not up to 21, that doesn't mean they don't have access. They could have access. So what about the one their parent bought, stuff like that? So, but the idea here is just like, okay, we actually want to measure the treatment effect after taking into consideration the threshold. And what we're trying to say, the mortality actually, we expect the mortality to go higher, and how much higher is 7.66 to 7, attaining the age of 21. That's exactly what I mean here. Okay, so when you want to see whether we should use a different slope scenario or not, because what I actually use to come out with this result is assumption of the same slope. But as you can see here, this is the first one. This is the slope of the first group, below the threshold C, and this is the slope above the threshold C, and the different and if you take a look at that, you're actually going to see the slope here is alpha 1, the slope here is alpha 1 plus alpha 3, and we may be thinking that, oh, they got different slopes. So if we actually want to use the idea that they had got different slopes, because you may want to say, oh yeah, the intercept here is alpha 0, but the intercept here is alpha 2, or maybe they actually necessarily have different slope or based on that. So if you actually we want to run that regression based on the idea of different slopes on the both side, we basically going to consider this this is the code. Okay, and after running the code, this is what I have. 7.6627. Let's see what we got before. We got 7.627. So which actually means it stay the same. Okay, whether you are talking about the same slope or you're talking about different slope. Okay, that very mortalities are actually stay the same. So what we're trying to say here is that reaching the age of 21, the mortality 100,000 of the participant, actually go out. I mean, it's 7.627 higher. Okay, so when we decide to modify the functional form, because in statistical analysis, the functional form is very, very important. Initially we assume in linear. What if we go quadratic, or maybe we want to make it more complex in a way? Okay, making it more complex in a way, we basically want to say maybe that will capture the relationship, very well. So this is the code, and in the end, the threshold actually go up by 9.5478. Okay, when you use that, so you can see the effect now. So the mortality is 9.5478 or higher. Okay, reaching the age of minimum age of drinking age of 21. And when we want to conduct what I call a sensitivity analysis, where we actually want to truncate, we don't want to use the overall range of the data. We only want to focus between the age of 20 and 22 years, and we're also removing the quadratic time. We want to focus on the linear, and let us see how does that change the trajectory of the result. And in the end, we realize the threshold is 9.573. So which we call the average treatment effect. So what we're trying to talk about is that the mortality, of the mortality, reaching the age of 21 now, the mortality is actually 9.753 higher. Okay, so of course, you can actually use the resources here by Carpenter, Christopher, and Carlos Dopp in 2009, where they work on the effect of alcohol consumption on mortality. Okay, don't forget we've actually worked on the effect of alcohol consumption on mortality, putting into consideration the minimum drinking age. Of course, we actually came to conclusion that effect is it's basically going to be positive, right? Except that, we have a different treatment effect, considering different module architecture. You get what I mean? But in each of that, is actually going to go, the mortality going to go higher. Okay, the mortality of those who consume alcohol, we actually go higher, attaining the age of 21, which is a allowable minimum drinking age in the United States. Okay, so this is where I'm actually going to stop. Is there anyone who want to ask question or any clarification before I go? Okay, so silent actually implies that you guys are good. Okay, so make sure you stay safe and have a lovely day. So bye for now, everyone.